the topic about dimensionality reduction in the machine learning. So let me show you PPT for more information. So in this main, I want to tell about introduction to dimensionality reduction and popular dimensionality reduction techniques. So, what is the definition and the importance? So, let us come to the what is dimensionality reduction. Dimensionality reduction refers to the process of reducing the number of random variables under consideration, simplifying the data sets while retaining the essential information. So, is the dimensionality reduction necessary? Dimensionality reduction we will do in the machine learning. So it is crucial for improving computational efficiency and enhancing model performance and eliminating redundancy, ultimately leading to faster and more accurate data analysis. So overview of the techniques. What are the techniques in the dimensionality reduction? In this mainly we have two techniques, linear techniques and non-linear techniques. Welcome to linear techniques. This involves the methods like principal component analysis, which means PCA, which project data into lower dimensional where preservance and variance, making interpretation easier. In nonlinear techniques, we will include the t-distributed stochastic neighbor embedding, which is in shortcut known as t-SNE, and UMAP, which capture complex data relationships in data, and linear methods may overlook, allowing for better visualizations. So let me tell more about PCA. PCA full form Principal Component Analysis. In this we have mathematical foundation of PCA. PCA is based on the concept of variance and linear transformations where it identifies the direction and maximizes variance in high dimensional data. Application of PCA in real world scenarios. PCA is widely used for image compression, reducing noise in datasets, and pre-processing data for machine learning, making complex data more manageable. T-distributed stochastic neighbor embedding. In the working mechanism of this is it converts similarities among data points into the probabilities, embedding high dimensional data into lower dimensional while preserving local structures and relationships. Advantages and limitations. In excels in visualizing high dimensional data, revealing clusters, but can computationally intensive and may struggle with large data sets and global data sets. This is all about the dimensionality reduction. In further, we can go to the Google Colab for practical knowledge. Let me show about the Google Colab. In this first one is dimensionality reduction. So I already told that dimensionality reduction is the process of reducing the number of input features in the dataset while preserving important information. So think that the compression of high dimensional data like 1000 column data set into smaller representation like 2D or 3D. So by this we can improve model performance, reduce overfitting and enable data visualization. As I already told that popular techniques like PCA, principal component analysis, which means it converts the data fewer dimensions into the maximum variance. So it is a unsupervised. So for this code, I have taken that iris dataset. We know that the iris is divided into three types, and in the three types, I am going to show that the dimensionality reduction. So first I took from SQL and decomposition import PCA. So SQL and dataset import load iris. Import matplotlib as PLT. It is a uh, pandas library for visualization the data. So in this I took that iris data set where X is iris data and Y is iris target. So by using PCA components to reduce the fit transformer and then I have loaded to show the graph. So now we can see the output of the graph by this code. So I already told there are three types. So by using that dimensionality reduction, it changes, it varies, and it given a spotted graph like scatter plot. So next one is t-SNE, t-distributed stochastic neighbor embedding for greater visualization cluster. This PCA is a linear method and this t-SNE is a non-linear method. So it preserves local structures of data. So we can see from SKLM manifold input t-SNE. So in this we have two components and perplexity is equal to 30. So now fit the data and transform it. Take the scatter plot and take XTNC, and these are the graph points. So we can see the finally visualization of the t-SNE visualization. I already told that we have three types in iris data. So we will get three points and scatter points. LDA is also another type of non-linear dimensional data. It is a supervised. It reduces the dimensions while maximizing class separability. Great for classification tasks. Autoencoders. Autoencoders is a deep learning model used for neural networks to compress and reconstruct data for good and large complex data. So in this, from TensorFlow Keras models, we will import the sequential and the dense. For more compressed data and to reconstruct data for using of us. It can be, if it is unwanted, it will be removed. If it is wanted, it can be used for further classification. So in this dense also we have given some graph, like we have given some limitations. So activation and input shape, all we have given. It is a linear, and how to fit that a pose and all we have given. So this is all about that, and real life uses of this is face recognition. We can use PCA to reduce the face image size before classification. So recommendation engines are compress user item data using matrix factorization. So this is an example where we can see we have given two qubits of x and y, and by using dimensionality reduction, I have divided first it is into 2D. This is actually 3D figure, so I have divided it into 2D and the single graph for better understanding. So and next code is to import all the libraries Matplotlib, Seaborn and datasets and decomposition and pre-processing. After that we have to load the iris and standard scalar and fit transform the iris data. So the target name is iris target names, and then apply PCA 2D. So the output will be in the 2D structure. So we have taken n components and fit transport, and t-SNE also in the 2D. So we have given the components, and we have perplexity and random state, and we have to fit and transform the data. So this is all about the plot data, so scatter plot. So we have used in everything scatter plot. So PCA iris data and the principal component 1, principal component 2 in next label y label. Finally we have to get the scatter plot, and this is for t-SNE. Same like that only, iris dataset component 1, component 2 and the class title. We have to get the scatter plot. So PLT type layout, and we have to show the data. See the output of the data. So this is the PCE of iris data, and this is the t-SNE of iris data. I have told you that we have three types of iris flavors, and these are named as 0, 1 and 2. So by using the PCA and t-SNE, it have given the output as this. This is all about the dimensionality reduction.